Having seen the strengths and the weaknesses of neural networks in the previous videos, we're now going to actually learn how they work. And you'll find whether this is a multi-layer perceptron, whether it is a deep neural network, or whether it's a convolutional neural network, they're all going to have the same basic principle in mind. You're going to start off with your input, be that a string of text or a table or an image, and we're going to compute a new representation of that input, and then we're going to try and classify an output based on that new representation. So this is a very basic neural network. It's called a multi-layer perceptron, and it starts with an input layer, which is going to be where you put your data in. We're then going to have a hidden layer, and this is what we were talking about before, where we don't know exactly what is going on within this layer. If we had all the time in the world and all the computational power in our brains, then we could work it out, but for the most part, everything that's processed in this layer remains hidden. And finally, we have an output layer where we actually perform the classification to work out what we think of the data that we have put into this network. And this is an interesting aside for any f of x, for any polynomial. A neural network can closely approximate that polynomial. So up until now, we've been talking about this perfect real-world function that we're trying to approximate. This is exactly what a neural network is able to do. And already this looks quite complex and quite abstract. So before I jump into any of the technical details, I just want to show you the code for this initial neural network. And you'll see that it's actually very, very simple. We have the input dimension, which is 3. So this is your input layer. And the first layer that we code when we're using Keras, we're just going to have to stipulate this input dimension. And then this number over here in green, this is going to be the output of the first layer. So that is going to be the number of nodes that you have in your first hidden layer. And then Keras knows that this is going to carry forward into the next layer. So you don't need to say input dim again. It just automatically does that. And you just need to tell it how many output nodes you are going to have. In this case, it's 3. For now, I don't want you to worry about this activation. We are going to talk about that in lecture 5. But for most of you, we're going to be using ReLU throughout all of the hidden layers. And then we're going to be using either softmax or sigmoid in the final layer. So now we're going to see exactly how we can actually calculate the nodes in the hidden layer. So we're going to use the exact same neural network that we saw in the previous slides. And we remember that the input layer is going to have an input dimensionality of 3. So we've got 3 nodes. That means what we're putting into this neural network is just going to be a 3-dimensional vector. So that's just going to be x1, x2, and x3. And we're going to call this input x. Now for each node in the hidden layer, we're going to create a connection to every single node in the input layer. And on those connections, we're going to place a weight. So for the first node in the hidden layer, h1, we're going to connect that to x1, and we get the weight W11. Exactly the same for the second input node. We get the weight W12 and then W13. Now remember, what you will actually be putting in with these x1s are just numbers, and these weights are also going to be numbers. So to calculate this h1, we use the following formula. We simply multiply the weight W11 by the corresponding input feature. So just some mathematical notation. We've already seen that this x is going to be represented as a vector. So we can use row-wise vectors or column-wise vectors. We'll choose which one of these is more useful to us, but it doesn't really matter that much. And then for this node h1, we're going to have a correlated weight vector, which is going to be W11, W12, W13. And to get this h1, we can just say that we have this W1 times x. So this is a dot product between these two vectors. We do the exact same thing for all of the nodes in the neural network, in the hidden layer, until we get to the final one. In our case, we've just got 4 nodes in this hidden layer, but usually you'd have more. Sometimes you'll even have 2,000 nodes in this layer. And you'll notice that we have a new weight for all of the new connections that we have between nodes. Then, once we've computed all of this, we calculate a bias term. And again, these are going to be worked out by the network the same way that the weights are going to be calculated by the neural network. These bias terms are sort of like a constant when you have the initial, like when you're doing GCSE maths, you have this y equals mx plus c. So the bias terms are kind of like this additional constant that we're adding on the end. The key thing to remember is that the bias term applies to each node in the hidden vector rather than each connection within that vector. So in terms of writing this system down in shorthand, because if you do any more reading or you go on to study neural networks in more depth, you won't see this represented in this longhand form, you'll see a shorthand form. So these x1, x2, x3, they appear in each of these equations for each node. So we're going to just write them exactly in the same form that we place them in a vector like this. So we're going to use a column vector because that's convenient for this. And you'll see that we have these W11, W12, W13, and then more W's for the next one. And this is actually going to look a lot like a matrix. Okay, so if you remember matrix multiplication from the first lecture, you go across the first matrix and then down the second one, and we consider this vector as just a 1 by 3 matrix. And it'll be W11 times x1, which is what we have here, plus W12 times x2, plus W13 times x3. Then we want to add the bias terms b1, b2 to bn. Can do that very simply because vector addition is a much more straightforward process. And you will actually end up getting your list of hidden nodes. So this whole system can be written in this simple equation where h is the vector that you obtain at the hidden layer, w or wt is the weight matrix that you're learning, x is going to be the input, and then b are going to be the bias terms that you're also going to learn.